All right, so last time, what did we start off with last time? Last time we started off with going over the integrated rate laws for 0th and first order reactions. All right, and so the integrated rate laws were different from the experimental rate laws. Why and how?
The integrated rate laws, the relationship between the concentration of the reaction and time.
Right, relationship between concentration versus time, right? Whereas the experimental rate laws were relationships between what? So if it was our arbitrary reaction, AA goes to products, it was A, versus time. The experimental rate laws, which is what you guys did in lab, and what we did a good amount on Tuesday and last Thursday. What two things did those give us a relationship between?
The concentration of the reactant
Mm-hmm.
and the rate of the reaction.
Yep, the rate of the reaction, so experimental rate law was between the rate of reaction versus the concentration of the reaction. Right, and we use this experimental rate law for first, 0th, and mobile digitase for second order reactions as well, to then figure out the relationship of the concentration versus time, right? And so the way we did that to make the experimental rate law is we knew that the rate of the reaction is equal to the rate constant times the concentration, and whatever the order of the reaction is also equal to what was the differential or the difference, the change in concentration per unit time here. And that was called, we don't have to do any calculus or anything like that, but that was called the differential form of the rate law. And you solve that, and then that gives you, one of two laws. For a 0th order, it was concentration at time t is equal to minus the rate constant times t plus the initial concentration. And then for a first order, so put 0, for a first order reaction, we had the concentration at time t, the natural log of that is equal to minus the rate constant times the time plus the natural log of the initial concentration. All right, so those are our two integrated rate laws that we went over. And so we initially started talking about the rates of the reaction, how that's related to the balanced chemical equation and the change in concentration per change divided by the change in time. Then we talked about the experimental rate law, good morning, which talks about how the rate of the reaction is related to the concentration. And what do? We just make up some, expression. We solve for the exponent there. That gives us the order of the reaction. And based off the order of the reaction, you can then plug that into this form of the rate law that allows you to solve for the integrated rate law equations. And with these, we went over one example where you're given the order of a reaction. If you're not explicitly given the order of the reaction, how could you tell the order of the reaction? Right, so we had a problem and it was like, oh, this is a first order reaction. What else would tell you the order of the reaction? What's one thing we always have to keep track of whenever we're doing anything with kinetics or really chemistry in general? the units, right? And the units of what can tell us the order of the reaction?
The rate constant.
The rate constant, right? So units of rate constant tell us order of the reaction. Right, so that's one thing we always have to keep in mind. All right, so we talked about the integrated rate laws, and then in lab we continued the lecture, so I know there's a lot of lecture on Tuesday. In lecture, what did we discuss? I'm gonna go to the next slide once we get a second to write. Or in lab, what did we discuss? All right, so this we're looking at the concentrate or the time dependence of the concentration of the reaction. What else do we look at? The dependence of what on what other variable? Yeah, the temperature and the rate constant, right? And the rate constant, which is then the rate of reaction, right? We also looked at the temperature dependence. Of the rate constant. And the equation that we used, which we didn't derive, was that K, the rate constant, was equal to a frequency factor times an exponential factor that had in its exponent e to the minus EA over RT. Right, so this was our rate constant, the same as in the integrated and experimental rate laws. A was our frequency factor. And then what were the other constants or variables we have here? T was the temperature. What was R?
The
Ideal gas constant. And then EA was the activation energy, right? The activation energy. And what this said was that, well, the rate constant is what changes as the temperature of the reaction changes. And what this says is that we have a frequency factor that says how often or what's the frequency that we're approaching the transition state. The transition state was what again? It is the most unstable state, right? Because if we had our little potential energy diagram, that looks something like this. Go from products to reactants, or reactants to products. Right, this quantity right here represents what? What was that? That distance between the reactants and products. This is the activation energy. And then if we were to look at the difference between the reactants and products, does anyone remember what that one was? From Chem 1A. That was the energy difference between the reactants and the products. This was the enthalpy, is usually what we're doing. And then in next week's lab, you'll be measuring that directly. Right, so the frequency factor that is how often are we approaching the transition state? The transition state is the state that's defined at the maximum of this energy curve. Right, so this was energy on the y-axis, and then the reaction progress on the x-axis. Right, so the frequency factor says how often we're approaching the transition state, which is also it's the most energetically unfavorable state, but also the state where once you reach that, you know, half the time you're gonna move back to the reactants, and the other half you're gonna move on to the products. So that's what the frequency factor described, and then the exponential factor. Does anyone remember what that was? What values is the exponential factor between? Yeah, 0 and 1, right? So the exponential factor, e to the minus EA over RT is always between 0 and 1, right? And this basically said what fraction of molecules that do reach the transition state or approach it actually have enough energy to overcome it, right? And this is related to kinetic energy or heat, the temperature of the molecules themselves, right? That's where all the energy is stored. And so we look at these two different factors in the exponential, and we see how they compare to each other, right? So when the temperature is really, really large, and the activation energy is small compared to that, that means that you have something that's something small divided by something large, that gives us a very small exponent. If this is very close to 0, then e to the 0 is equal to 1, right? So that means at the very high temperature limit, we get exponential factor approaching 1. So that means that this transition, almost every single molecule is going to have enough to at least overcome the activation energy. If the temperature is low compared to the activation energy, we're in the low temperature limit. That means this is going to be like something like e to a very, very large number, like infinity. So you have e to the minus infinity, right? Which is something like 1 over e to the infinity. This goes off to infinity. 1 divided by infinity is like saying it's equal to 0, right? So that's why then it goes really low. So in the low temperature limit, this goes down to 0, so then the rate constant is 0. If the rate constant is 0, what's the rate of the reaction then? All right, let's think about our experimental rate law. Right, if the rate constant is 0 here, what's the rate of the reaction going to be equal to? So if little k is equal to 0, right, then that means that the rate of the reaction, which is large k, is also going to be equal to 0, right? So if this is 0, then the rate of the reaction is 0, which makes sense. If we don't have enough energy to actually make the reaction proceed, then the speed of the reaction should be close to 0, right? It's like if you have someone who's trying to run uphill, but they don't have enough strength to actually, lift their legs, or not gonna be able to run up the hill at all. All right, so that's where we ended last time. Does anyone have any questions about what we discussed or where we ended up? Right, so there's a number of different relationships that are all intimately related to each other, but they tell us different things, right? Our experimental rate laws tell us between the rate of the reaction and concentration. The integrated rate laws tell us the concentration and how that depends on time. And then the Arrhenius equation, which I'm going to try and attempt to spell right here. This is called the Arrhenius equation. That tells us how does the rate of the reaction depend on temperature, specifically by looking at the rate constant, because that's where the temperature dependence shows up. Thumbs up, thumbs to the side. Okay. All right. So we'll take a second, just talk about significant figures and logarithms. So when you're dealing with logarithms and anti-logarithms, which is just exponentiating something, the number of sig figs and I'll put here, we say in the mantissa, which is just a fancy way of saying what's inside the logarithm. The number of sig figs in that logarithm tells you the number of decimal places in your answer. All right, so if you have 3.6, we have 2 significant figures, and that means that we have 2 decimal places in our answer. And so we're going to be using logarithms a lot throughout the semester, especially once we get to acids and bases, which is coming up after. That's our next chapter. And then it also goes the other way. So if you take the exponential of 5.3245, and I'm going to plug that in right now because I don't know what that is. So we have 5.3245. Then we exponentiate that. That gives us 205.305682. We have 4 decimal places, which means that we need 4 significant figures in our final answer. 4 sig figs in the final answer. So the final answer would be, morning Andrew, 205.3. So it goes both directions, right? However many decimal places you have in your thing that you're exponentiating, right? Exponentiating is just that's the definition of what an anti-log is. And really it's the log, which is the anti-exponential, the inverse of the exponential operation. Okay. All right, so here we have an example. We have cyclobutane, which is a cyclic organic molecule. You guys have plenty of practice that next semester in your no-chem. So this reaction is going to be first order, right? So that's telling us something relevant. In an experiment, the initial concentration was found to be 0.0015. After heating at 450 degrees Celsius for 455 seconds, the reaction, the concentration was reduced to 0.00119 molarity. So based off this information, determine the rate constant for the reaction at this temperature. Right, so here we have temperature, and then we're also told that as first order, you're given an initial and final reaction. After, and also you're given time. So take some seconds, just take some time to see what's the relevant information given to you, what do you need to use, and then based off of all the different rate laws, experimental, integrated, Arrhenius equation, what might you need to use to solve this equation? Right. Why is the order relevant for this? Yep, it says this tells us which equation to use. The fact that we have C4H8 at a certain time, the initial concentration, and the time it took, that tells us that we're going to use, of the 3 types of equations that we talked about, experimental, integrated, or Arrhenius equation, which is that? Which of those are we going to use? I think you already said it down. The integrated rate law, right? Integrated rate law, right? So this tells us that we're going to use the integrated rate law. How does it tell us that? Well, it gives us all of the variables in that equation we need to then solve for the rate constant, right? We want to solve for lowercase k here. So why don't you guys Why though? Oh, it's still. It says it's still screen recording. I'm just gonna write the first order integrated rate law was ln c4 h8 at time t equals minus kt plus ln c4 h8 initial. So we have our integrated rate law, which was natural logarithm c4 h8 at time t equals minus kt plus natural logarithm c4 h8 initially. Right, so we need to solve this for k, right? Because we want to solve for the rate constant, so we have to isolate that variable. So we subtract ln c4 h8 initial from both sides, ln c4 h8 initial from both sides, and then we can use the way that I'm going to go through this algebraic. You don't have to do this exactly the same way. If you did a different one, you still got the same answer. That's fine. So we subtract that from both sides. On the right hand side, what happens to the logarithm of the initial concentration? Those go to 0, right? And then now we're left with ln c4 h8 time t minus ln c4 h8 initially equals minus kt. To isolate k, what do we divide both sides by? Divide it both sides by minus t minus t. We can also combine the logarithms in the numerator. Does anyone remember how we do that? Yeah, it becomes the logarithm of the ratio of them, right? Of this one over that one. So this becomes, after I cancel out the t on both sides and the negative sign, this becomes ln c4 h8 time t divided by c4 h8 initially all over minus t is equal to the rate constant. And so I did it all algebraically at first because, okay, I know I'm solving for this, and now I just have to determine where each of these concentrations go. Right, so for the time, what do we plug in? Yep, the time is going to be 455 seconds, so I'm going to just extend this over here. 455 seconds. We keep our units there. And there's something we can notice from the units just by looking at this, right? What should the final units of our answer be here? Inverse seconds, right? Which makes sense because for a first order reaction, k needs to have units of inverse seconds, right? We have the logarithm of these two things, which have the same units, so those cancel out. Whenever you have a logarithm, that's going to be unitless in general, right? So there's no units in the numerator here. And then we have ln, the concentration at time t. Here we have a time t is 455, so that's why the subscript 455 is there, is 0.00119. So that's 0.00119 molarity over the initial concentration, which was 0.00150 molarity. And so we can plug all that in. And it looks like a small number divided by a larger number in the numerator, so that's going to be less than 1. So that should give us a negative answer. And so the negative signs will cancel out, right? Our rate constant has to be a positive quantity, but the negative sides will cancel out because of what's in the logarithm. 0.00119 divided by 0.0050. Then I can take the logarithm of that. It's a negative number divided by 455. So that gives us, that's 3 sig figs here. The number of sig figs the mantissa is 3. So then that'll be 3 decimal places. So it'll be 3 sig figs. So it'll be 5 times 1, 2, 3, 4. 5.23 times 10 to the minus 4 inverse seconds is what our rate constant should come to. Did everyone get something similar? Did I make a math error somewhere? Or you guys get something around there, right? So it depends. If you plug in numbers up here and then solve for everything, depending on how many decimal places you're going to carry, you might get something that's slightly different. So I know a lot of you guys are getting different answers from your lab partners in lab. That's just because the logarithms, the way decimal places carry an exponential, kind of grows pretty fast, right? So error can propagate pretty fast. In general, I hold everything till the end. That way you get the most accurate answer, but if you did it earlier, I'm not going to mark you down for something like that. Okay, so here was just some algebra, some rearrangement, and having to recognize what equation do I have to use, right? Because it's kind of the list is getting a little large, right? Like we already have, 5 different equations that we're choosing from, and then we're going to add another 4 or so to that list. So the list of them is getting large. We have to be able to look at the problem and identify what equation we need to use there. Okay, any questions on this? How's everyone feel? Thumbs up, thumbs side. Okay. It's okay to put thumbs to the side or thumbs down if you guys don't feel that comfortable with it just yet. Okay, so now we'll talk about half-lives. So generally we talk about half-lives right after first order reactions. Does anyone have any prior knowledge, or what do they think of when they think of half-lives? Sometimes you may have heard of it in terms of radioactivity, right? So radioactive processes have half-lives. And once we do a little bit of nuclear chemistry later in the semester, you'll learn that all nuclear decay processes are first order reactions, which is why the half-life looks the same. Also, if you think about the time a drug remains in someone's body, usually they talk about half-lives. And so all a half-life is the time it takes for the concentration to decrease to 1/2 of its original value, right? So that just means that after a certain amount of time, the half-life is defined as when the concentration is 1/2 its initial value. And so we'll go through how to do this, and so this is one thing I do kind of want you guys to be able to do, just a little bit of algebra, because if you're given any arbitrary order reaction, you should be able to solve for the half-life. You can always memorize the equation or write it on your equation sheet, but if you are given the integrated rate law for whatever reaction it is that you're looking for, you can always solve for the half-life. And the process for that is pretty simple. So you just start with, this would be our integrated rate law for what order reaction? First order reaction, right? That's our first order reaction rate law. The only thing they did there is they switched some of the negative signs around, but that's fine. Oh, wait, no, they didn't. They did. This is the same as what we did. And then you define the concentration at time t to be 1/2 the initial concentration. All right, so we're defining this right here at 1/2 the initial concentration. When you do that, you have ln is equal to A0 1/2 divided by A0 is minus K times T sub 1/2, right? And so we'll use, and what you'll see a lot, T with the subscript 1/2, that's what people use to signify the half-life of a reaction. And so how can we simplify the left-hand side of this equation then? Right, so we replaced A at time t with 1/2 times the initial concentration. Right, so if we have the initial concentration, one in the numerator, one in the denominator here, what happens to them? They cancel out, right? So we get these two cancel out. So we're left with ln 1/2 is equal to minus k t 1/2. And we just want to solve this for t 1/2. And that'll give us the definition of the half-life. Right, so we divide both sides by minus k. This becomes ln 2 over k equals t 1/2. And the only identity or rearrangement, what's the logarithm identity for a fraction again? If you have a quotient, that becomes, yeah, the subtraction of the two terms, right? So you get ln 1 minus ln 2. This equals ln 1/2, right? Let me write that a little bit better. ln 1/2, that's just using the identities that we've been using. And natural logarithm of what? Of 1 is what? 0, right? And that's because what's the logarithm asking? It said e to the what is equal to 1. And so, right, so we're saying e to the what is equal to 1. Well, whenever we raise anything to the power of 0, it's equal to 1, right? So ln 1 is equal to 0. So then if you divide this by minus k, right, this goes to 0, so you have minus ln 2 over negative k, so that's how the negative signs cancel out there. So these negative signs end up canceling out, and that's how we're left with our expression for the half-life. I don't think I have a... And so the half-life can also tell us how does the, or how the half-life can be dependent on the concentration or not dependent on the concentration. And so in this case, would you say the half-life is dependent on the concentration of A in this case? Or the initial concentration? Right. It doesn't show up anywhere in this expression right here, right? So you'd say the half-life is not dependent on the initial concentration. So that means for a first order process, every time you go through, the half-life stays the same no matter what as the process continues, right? It takes just as long, so you get half the concentration, you wait the same amount of time, then you half the concentration again. You wait the same amount of time, you half it again and again and again and again, right? For other order reactions though, that might not always be the case. Because here, for first order, we have t 1/2 equals ln 2 over k. And does actually, one other thing I'll ask you guys, just to put in your head, is do the units for this make sense to you guys? Right. Half-life, what do you think the units of that should be? Time. It should just be in seconds, right? The units of the half-life should just be in seconds. Why? Because they're asking how long something takes, right? How long does it take for you to half the concentration? For a first order reaction, k should be units of what? Inverse seconds. So in the denominator here, we have a 1 over seconds, right? If that's in the denominator, that means overall this has units of what? Seconds, right? If it's 1 over seconds in the denominator, then we bring that up to the numerator, we have seconds. All right, so what I was saying is 1 over seconds is the same thing as just seconds. And so what about other order reactions? So we haven't talked about a second order reaction yet, but we have talked about a 0th order reaction. Does anyone remember what the integrated rate law? So the thing with the half-lives is you always start from an integrated rate law and go through the same process that we just did, right? You say that A at t 1/2 is equal to 1/2 the initial concentration. And then you solve for t 1/2. So for a 0th order reaction, Right, zeroth order reaction, how should the concentration versus time look? What kind of plot should that look like? More simple types of lines that we look at. It's just a line, right? It was a linear relationship between concentration and time, right? And so the zeroth order reaction was A at time t is minus kt plus A initial concentration. Right, so that was our zeroth order reaction. So why don't you guys take a second and see if you can figure out what does the half-life for a zeroth order reaction look like? And then think about then, does it depend on concentration or time at all? As t 1/2 is equal to something that depends on either the rate constant and maybe the initial concentration. Is we replace this with 1/2 concentration initial equals minus kt plus concentration initial. Think about what was the first step that you guys did from here? Go ahead. Yep, we subtract the initial concentration of A naught from both sides. Right, and so that gives us 1/2 minus equals minus kt, and that simplifies, what does this simplify to? Minus 1/2, right? So this gives us minus 1/2 A0. That should signify, okay, this is starting to make sense because, right, time is only a positive quantity, so it should be positive, right? So that means that these negative signs will cancel out now, right? So that tells us, okay, that something's going right here. And then we can divide both sides by minus k minus k. And so the negative signs cancel out. We can bring the 2 into the denominator as well, and we get A naught over 2k is equal to t 1/2. All right, so it's not a whole lot of steps, but I know for a lot of us this is the first time we're kind of asked to find an expression of something, right? So this is the first time that we're kind of being asked, okay, solve for what the equation actually looks like here. So you might be, okay, what can I do? What am I not allowed to do? It's the same thing as if we're solving for k or t in the previous problems that we've done, except now we're just leaving it in this form instead of actually plugging in numbers just yet. And so does this depend on the initial concentration? It does, right? It says that, how would you say these two are related to each other? Inversely or directly proportional to each other? Directly, and so if you increase the initial concentration, what happens to the half-life? Does it increase? If this goes up, does that go up? Yeah, that goes up. So if they both go up, right, then they would be directly proportional to each other. Right, so that means that as you increase the initial concentration, the half-life also increases. And for, the plot of concentration versus time, how we can rationalize this a bit is if this is our concentration, this is time. For a zeroth order process, it's a line like that, right? And what's the slope of this line? Yeah, the change in concentration over the change in time, and it's proportional to the rate constant. All right, so it's proportional to m equals, it's directly proportional to the rate constant. So if we just keep the slope the same, and then we're just adjusting the initial concentration, that means we're just sliding this line up and down, then for the time it would take for you to reach half the initial concentration should go up or down depending if you're sliding this up or down, right? This point right here is the initial concentration. Because it's just a line, if we just slide the line up, it's going to take longer for it to reach half of its initial concentration. And so this does depend on the initial concentration. All right, so first order reaction, the half-life stays the same no matter what your concentration is. For zeroth order reaction, the larger your initial concentration is, the longer the half-life is. That also means that as the reaction proceeds, what happens to the concentration of A here? As the reaction is happening, what happens to the concentration of A? Does it go up or does it go down? It goes down, right? So that means that as the reaction is progressing, the half-life is getting shorter and shorter because every time you half the reaction, you're starting with half the initial amount you started with at time equals 0. Okay. Any questions on this? Like I said, I know this is a little bit foreign to a lot of us solving for a functional form like that. Okay, so how can we visualize this then graphically? Well, if we have a first order reaction, right, at time equals 0, we want to go to half the initial concentration. So if we start at 1 molarity concentration, the time it takes to get to half that value, this is 1 half-life. For first order reaction, it doesn't depend on the initial concentration, right? So then if we're starting at a concentration of 0.5 molarity, to get to then 1/2 that concentration, it still takes the same amount of time. That has to do with the shape of this is a plot of the concentration versus time, right? So because of the shape of the curve, even though the change in concentration is getting smaller, the time it takes to reach half that value stays the same. So for a first order reaction, it doesn't matter how long or how much you start with, it's always going to have the same half-life. For a zeroth order reaction, and again, we focus on first order a lot because first order reactions is important for nuclear decay, which we'll focus on more later in the semester. But for a zeroth order reaction, since we just derived this, this is what it looked like. And this was our initial value of 1 molar. It's our concentration of A. And this was 1/2 that value. All right, this would be T 1/2 initially. All right, so we went down to 0.5 molar. And then from here, we go down again to 0.25 molar. You can see right away that when you do this, these are straight lines, so even though it's not exactly 1/2 right here, this line is perfectly straight. You can see right away that this half-life is smaller than the first half-life. Right, so since that's smaller, that means that, okay, it depends on the concentration that we started at for the half-life as they happen successively. So for something like a zeroth order reaction, let's say it's a drug in your body or something, that means that once you reach half the concentration, the time it takes for the rest to kind of start leaving your body gets faster and faster. Go ahead.
Does it say little box?
In the little box? Oh, the T, they're both supposed to be T1/2. That one, is that what you're asking about? Yeah. So this is the first half-life, and this is the second half-life. And when I say first and second half-life, what I mean is if we started with a 1 molar concentration, the first half-life is the time it takes to reach to 0.5, half of that concentration. Now it's saying, okay, we started at 0.5 concentration. How long does it take to reach 0.25 concentration? So that's the second half-life. And if you kept doing that over and over, you would see that that gets smaller and smaller because the triangles are getting smaller and smaller. Whereas for a first order reaction, because the way the slope starts to decrease as the reaction goes on, right? The slope's getting like flatter and flatter. That half-life stays the same for each reaction, for each time interval, or each concentration interval. So that's what I mean when I say we have like these successive half-lives, which is why radioactive decay can take so long, because the half-life really doesn't change, as time goes on. The half-life to reach half that concentration is the same amount of time. So if the half-life is 1 million years, to get to half the concentration, to get to half of that, it's going to take another 1 million years. To get to half of that concentration, then another 1 million years. Whereas like the zeroth order reaction, it takes 1 million years for the first half-life. The second half-life might take 500,000 years or something. So it gets shorter and shorter to keep halving the concentration. Okay, so let's take a break. Take like a 12-minute break right now. Back at like 9:47, and then we'll continue talking about half-lives. We'll go over some examples. This one's an explicit one. A lot of it's kind of plug and chug. This one's like a realization one. And then we'll talk about second order reactions. All right, so we talked about half-lives. For depending on the order of the reaction, the half-life can depend on the initial concentration or not. And that will also tell you that as the reaction proceeds, how much longer is it going to take for the next half-life to occur, right? So here we have an example. So we have nitrogen peroxide. It decomposes when heated. The rate law is first order in nitrogen pentoxide, not peroxide, with a rate constant of 6.2 times 10 to the minus 4 inverse minutes. What's the half-life for this reaction, right? So let's say it didn't say that it was first order. How would you know that it was a first order reaction? Inverse minutes, right? The rate constant has units of inverse time here, right? So it's not inverse seconds, it's in minutes here. You can always convert that to seconds. And so that's what I would like you guys to do as well. What is the half-life? And I'll put in seconds here, right? Because we have two different half-life equations now, so you do need to know the order of the reaction. So the first thing, we'll convert the rate constant, K, to seconds. So we can take 6.2, so if we just take a second to remind ourselves on how to do unit conversions, this is like 6.2 per 1 minute, right? And how many seconds are in a minute? 60 seconds, right? So per 1 minute, we have 60 seconds. So this is gonna end up with units of inverse seconds. The units of minutes cancel out, which is good, right? We still need inverse time for the unit, so we get 6.2 divided by 60 times 10 to the minus 4. Just plug that in. 6.2 divided by 60. So it gives us 0.103 times 10 to the minus 4 inverse seconds, which is like 1.03 times 10 to the minus 5 inverse seconds. Okay, and then we know it's a first order half-life, first order reaction, so then the half-life for that is equal to what? Alright, what was the equation for the half-life for a first order reaction? Yep, it's T 1/2 equals ln2 over K, right? And so this is K, so we just plug this into our calculator. 2 natural log is equal to 0.693 over 1.03 times 10 to the minus 5. Inverse seconds, so our final unit should be in units of what? Time, right? Because we have 1 over seconds in the denominator, so that means our overall unit should be time. So that makes sense because we're looking for a time that's what we're solving for. So 1.03 times 10 to the negative 5. So this gives me 6.73 times 10 to the 4 seconds. Did everyone get something similar? Good. Right, so this question, and most half-life questions, unless they're layered, this is just asking explicitly about a half-life, is relatively straightforward. Right, you can see how these questions can get relatively layered if I gave you a data table to then figure out the order of the reaction. Then once you had the order of the reaction, then I said, okay, well, if this is the initial concentration and this is the final concentration, this is the time it took, find the rate constant, and I said, okay, what's the half-life for this reaction? Then it could be a relatively layered problem going from one equation to the next. All right, any questions on this? Straightforward, thumbs up, thumbs aside. Okay. All right, so here we have a first order reaction, has a half-life of 26.4 seconds. How long does it take for the concentration of the reaction to fall to 1/8 of its original value? All right, so this is more of a conceptual type question. There's a little bit of math involved, but it's a conceptual question, asking us if we really understand what the half-life is, right? So given the half-life for a first order reaction, and you want the concentration to fall to 1/8 its original value. Oops. Next part. You have any approach for this problem? There's probably a couple different ways you can do it. One is very long and one is very short. Then what's the short way to solve this problem? Multiply it by 3, right? And so the reasoning for that is because 1/8 its initial concentration is equal to 1/2 times 1/2 times 1/2 the initial concentration, right? So this is 1 half-life. Then we multiply it again by 1/2. Oops, let me use a different color. That's the second half-life. And then this is the third half-life. Right, so each time we half the concentration, that's like another half-life that goes by. And so how come we can just multiply this by 3 then? What else in the problem tells you that you can just multiply this by 3? Because it's a first order reaction, right? And what do we know about first order reaction half-lives? It stays the same, right? Every time that we half the concentration, it stays the same. It doesn't depend on the initial concentration at all, which means that each half-life takes 26.4 seconds, right? This means that each half-life takes 26.4 seconds. If it was a 0th order reaction, then the half-life would decrease as the concentration decreased, right? So the first half-life would be 26.4. The second half-life would be a different half-life. We would need to know the rate constant to get the second half-life. And the third half-life would be even smaller than the second half-life. Right, and again, when I'm saying first, second, third half-lives, that just means the successive half-lives that are happening. For first order reaction, each half-life stays the same. So that means that 26.4, that the time for 1/8, the initial concentration, is equal to 3 times 26.4 seconds. So that should give you 78 or something like that. 3 times 26.4. 79.2 seconds. I think to actually do the long way, you'd actually need more information, right? So if you were given the rate constant, you could then also know, the same way we solved for the half-life, we would say 1/8 the initial concentration is the time after, time 1/8 of its original value, and then you could solve for that time as well. And then divide that by the length of a single half-life, and that would give you the number of half-lives that have occurred. Okay, any questions on that? So again, this is, like I said, most likely when you see this, it'll be part of a much larger problem, but it's relatively simple calculation. So this would be like something kind of more multiple choice oriented on an exam. Okay, so here we have a nuclear decay process. So this is pretty, this is actually a more layered problem. You're given a half-life of about 4.5 billion years. So it's how long would it take for 10% of the uranium-238 atoms in a sample of uranium-238 to decay. Right, so we're asking how long is it actually going to take to reach 90% of its original value. So the strategy here, right, and remember I mentioned this, but we're not going to talk about nuclear chemistry. All nuclear decay processes are first order reactions, right? So they're first order processes. And we're given the half-life, but then we're also asked to solve for, what are we actually looking for here? What's the answer? Yeah, we're looking for, what we're given is T1/2. We're given I'll put uranium-238 at time t, and we're given uranium-238 initially, and we're given it in a kind of convoluted way, and we're wanting to solve for the time it takes, right? But we're looking for a value that isn't a half the initial concentration, right? We're saying 10%. So we have to think about how are we going to use the half-life, the fact that it's a first order process, to then find the time it takes to reach a specific concentration, right? So does anyone have any ideas what relevant equations we might need for this? So because we know it's a first order process, right, that means all the equations are going to be related to first order processes, right? So this tells us they're all going to be all first order processes. So if they're all first order processes, what do you think we're going to need to use here? Given that we want to solve for time, we're given the half-life, and concentrations. Like I said again, we're given the concentrations in a more convoluted way. Anyone have any ideas? If we're solving for time, usually what do we need? What equation? In relation to concentrations. Integrated rate law, right? So one we're probably going to need to use is integrated rate law. So that's going to be ln concentration of uranium-238 time T equals minus KT plus ln uranium-238 at time 0. Then what else? So if we're looking at this equation right here, so we say, okay, we're looking to solve for a time, so that means that we need to use the integrated rate law, right? Because we're given, in a convoluted way, the two concentrations, right? We want to solve for time, so that's going to be our final answer. So what are we missing from this equation? What are we not given? The rate constant, right? So does anyone have any idea how we can get the rate constant? What else are we given? You're given a time, right? And what specific time? What are you given? What is that time? What is it defined as? We're given the half-life, right? Is the half-life related to the rate constant? Right, the half-life for a first order process was ln2 over the rate constant, right? So these are probably the two relevant equations we need to use and then solve for the total time. So why don't you guys take a second and see if you can at least get to a point where you just need to plug things in. Right, so solve for, once you have the rate constant, then you can use that with the first order integrated rate law to then solve for the time. The other thing I said is that they give you the concentrations here, but they give them to you in a kind of convoluted way. Right? And so this is actually similar to how we solved for the equations for a half-life, right? Remember when we did the half-life, we said, A at T 1/2 is equal to 1/2 the initial concentration, right? That's how we derived the half-life. We said this relationship right here, right? The concentration after a half-life is equal to 1/2 the initial concentration. Here we want to say, well, how long does it take for it to have 10% of the atoms decay, right? So how much of the original atoms should be left over? The original uranium-238. Or what percentage of them? 90%, right? So we want to say how long does it take for 10% of them to decay, right? So this information right here tells us that this is asking how long for the concentration after time t should equal what times the initial concentration? Like how would we put that mathematically that we have 90% of the uranium atoms left? All right, so we're saying how long for uranium 238 at time t to equal something times the initial concentration, right? The half-life was 1/2 the initial concentration. For 90%, that should be what times the initial concentration? 0.9 times the initial concentration, right? So it should be 0, I'm going to put this up here, 0.9 times the initial concentration, right? Because we have 90% of it left, right? So the initial concentration is 0.9, which is smaller than the initial concentration. So we have 90% of the concentration left. So now the same way when we solve for the half-life equation, you can use this relationship, right? Plug that into here to then solve for the time. So why don't you guys take a second and see if you can figure that out. And so we can actually set up, even before actually solving for the half-life, we can set up the second part, right? So we want to use this relationship, 238 at time t is equal to 0.9 uranium 238, right? This is our initial, right? This is our 90% of our original uranium 238 is left over, right? So that's what we got from that, and a little bit of information from the problem. And so our integrated rate law is ln U238 time t minus kt plus ln uranium 238 initially. So we can, because of this relationship, just plug that in for that expression right there, right? Because that's equal, you just plug it in, and the same way we rearranged it before, we can do that again. And when you get the ratio of the logarithms, the initial concentration cancels out, right? So let's go through that step real quick. ln, now 0.9 uranium 238 initial. So all I did was I just plugged it in for that initial value, minus kt plus ln uranium 238 initial. We can subtract the uranium 238 from both sides, ln the initial concentration 238 from both sides. What happens to the logarithm terms on the right hand side? Cancel out, or these go to 0, right? Because it's one number minus itself. So we get ln 0.9 238 uranium 238 initial minus ln uranium 238 initial equals minus kt. And what do we do with these two terms? Like, how do we simplify that? Yeah, they become the logarithm of the quotient of both of them, right? So this becomes ln uranium 0.9 uranium 238 initial over uranium 238 initial equals minus kt. And then how does this simplify from here? Yep, these two cancel out because they're the same thing. That's the same initial concentration. So we get ln 0.9, which is going to be a negative number, equals minus KT, divide both sides by minus K. Cancels out, and we get T is equal to ln 0.9 over K. Oh, minus. Oh wait, no, yeah, minus sign. Just doing a step in my head. All right, so once you get to this step right here, you can plug in what you solved for the new rate. All right, once you have the half-life, or if you wanted to do it algebraically, you could just solve the half-life equation for T1 half, which is what you're given. So we know T1 half equals ln 2 over K. That means K equals ln 2 divided by the half-life. You could plug that in for that right there as well. And that way you can just solve for everything in one term. You don't have to do multiple calculations here. So that would give you T equals minus T1 half ln 0.9 divided by ln 2. And if you plug all that in, that would give you the same answer. And you could leave this in units of years if you wanted to. You wouldn't have to put it in seconds. If you had rate constants and things that had mismatching units, then you have to make sure to take into account the units matching up. Right, and honestly, for anything with nuclear decay or first order processes, whenever you're given some percentage, like this is actually the hard step right here. Is okay, this is 90% of the initial concentration, and then once I have it in there, then rearranging everything, that's just math, that's just algebra. You get that with doing this enough times, but this realization right there that's the hard part when you look at the question. Okay, what is what is this actually telling me? And see what I get when I plug in everything. So I get, that's my calculator. We get the half-life was it 4.5 times 10 to the 9? 4.5 times 10, no, times 10 x to the y, 9, and then times parentheses 0.9 natural logarithm in parentheses divided by parentheses 2 natural logarithm. And I get that it takes around 6.84 times 10 to the 8 years. Did everyone get something similar? Okay. And so does this make sense? Does that answer make sense to you guys? And if it does make sense, why do you justify that value? How does that compare to a half-life? For this. What was the length of a half-life for this question? Huh? Yeah, 4.5 billion years, right? And this one is 684 million years. So is that larger or smaller than a billion? Smaller, right? And why does it make sense that number is smaller? Because you're only losing 10% of it, right? It should be less than a half-life, because a half-life you lose 50% of the initial concentration. Here we're only losing 10%, so it makes sense that this is going to be smaller than the time it takes to lose 50%. Right, especially with these questions, if you flip the percentages and do something like that, you can mess up. And for example, if you put 0.1, that's a common mistake, 0.1 times the initial concentration, And so why might you do that? Well, because on the previous page right here, it says 10%, right? So that's the percentage you see, but really that means there's 90% of what's left over. So if you put 0.1, then you'll get an answer that's like, 500 billion years, which is a lot larger than one half-life. But you're like, wait, this is, only 10% has disappeared. This should be a lot smaller than a half-life. Okay. So this is a more, typical free response exam style question where you're given a couple different things that you have to then use information and a couple different equations to get to the final answer. Right? So we have to start looking for the connections between them. What information are we given, and how can we use that, to find the answer we're looking for? And then again, we make sure the units work out here. We want to solve for a time. We're left over with units of years. And we do it in this expression. You see how that works out nicely because a half-life is units of years. Both of these don't have any units, so it should match. Those units will match. Okay. Any questions on that? I know this is this is like a longer problem, and it's I think can be a little difficult or challenging to wrap your head around too. Right. So the big realization here is just the 90%, 0.9 the initial concentration, and we'll have more practice doing it. Okay, so we only have about 4 minutes left, and so we've talked a little bit about this leading up to this point, is graphing the different order reactions, right? And so when we are trying to determine the order of the reaction, we can also, and you guys will do this in a future lab experiment, plot the concentration versus the time. And based off the type of plot, that'll tell you whether or not the reaction is 0th, 1st, or 2nd order. You're really only going to be testing for those three because we would have to go through a whole different differential equation to solve for anything else, right? So you're only testing for 0, 1st, or 2nd order. And we can write the integrated rate law for a first order reaction as ln concentration at time t is equal to minus kT plus ln the concentration at the initial concentration. And so we said that there's a specific way that you can plot this to then get a line, right? Remember we talked about that on Tuesday. And so how would we plot this to get a line? What's our independent variable and what's going to be our dependent variable? Right, independent variable just means that's the variable that doesn't depend on anything else. So something like time, temperature. The dependent variable is whatever the function is or what it is that we're actually measuring. Right? So what are we measuring as time goes on? The concentration, right? So the concentration is going to be related to our dependent variable. If we want this to look like a line, we can plot the logarithm of our concentration at that time versus the time, which is our independent variable. The slope is equal to minus the rate constant, and the y-intercept is the natural logarithm of the initial concentration. And so what does that actually mean when we're plotting something like this? That means that, let's say you measure the concentration of 0.2 molar at some time, right? That means your data point, when we're plotting it, is going to be, you're going to take the logarithm of 0.2 and plot that versus 10 seconds. Let's say it was after 10 seconds. Right? Then you get the next data point, take the logarithm of that concentration, you plot it versus the next time interval, which is maybe 10 seconds after that. And when you do that, if it is a first order reaction, it should give you a straight line. Right? So what we're doing is we're manipulating the data in a way that if it is a first order reaction, it should be a line if we plot the data this way. And so this is another way that you can measure or determine if it's first or second order. When we use the experimental rate laws and determine the coefficients, that's saying how does the reaction rate depend on the concentrations, and the order is related to the exponent that you're solving for. Here, let's say we only have concentration versus time data, we can't measure the rate of the reaction, then we can determine the order by plotting it different ways and seeing which one looks like a line. Right, so again, we have a straight line for a first order reaction when we plot the natural logarithm of A versus time, and a slope of minus k, and a y-intercept of the natural logarithm of the initial concentration. And so this is just kind of repeating what I just said, but for example, we have plotted the data of the concentration versus time of SO2Cl2. And if we plot the data in a way, and we know it's a first order reaction, then we know it should come out as a line. If it is not a first order reaction, then it will deviate from that line. It will not look linear. And we'll stop on the next page for today. We'll finish up plotting first order reactions and talk about second order reactions on Tuesday, and then get into reaction mechanisms and elementary reactions next Thursday. Okay, so when you plot this, I'll go back in a second, but when you plot this, right here, so we plot the logarithm of the concentration, meaning that each of these data points, we've taken the logarithm of the actual concentration and just plotted that versus the time. So it sounds complicated, but really you're just, if you were in an Excel worksheet, all that you would do is you would just make a function, ln of the cell before it, and then copy that for all the cells below it. And we'll have some practice working with Excel or Google Sheets or whatever you want in the next lab doing that. All right, do you guys need me to go back to the previous slide? Because it's just a lot. Okay.